Welcome to this lecture series in real analysis. In this lecture, we'll talk about compactness, which is a most important concept in all of analysis and in fact in all of mathematics. So let us recall what we need. You will need the notion of an open cover. So a subset, suppose we are given a subset A of R, then a collection of subset C of R. So every element of this chi is itself a subset of R. We say this is a cover of A if A lies in the union of all the things that are there in this collection. So that's the definition of a cover. We say this is an open cover if, first of all, this is a cover, and secondly, every element of it is an open set. So that's an open cover of a given subset. A subcover of a given cover is just a sub-collection, which is also a cover. So suppose C is a cover of A. A subcover of C would be a sub-collection, meaning a subset of C, such that this subset is also a cover of A. Okay, and we saw the Heine-Borel theorem, which says that if we have the closed interval, finite, or rather I should say bounded closed interval, meaning A and B are real numbers and we are considering the corresponding closed interval, and we pick any open cover of it, then there is a finite subcover of this open cover, meaning there is a finite subset D of C, which is also a cover of it. So every open cover of a bounded closed interval admits a finite subcover. That is the Heine-Borel theorem. And with that, let us proceed. Here are some problems for practice. And now let us get started. So we will define the notion of a compact set. This will be a rather abstract definition motivated from the Heine-Borel theorem. Whatever was the conclusion of the Heine-Borel theorem, this definition will stipulate the same on an arbitrary set. So fix a subset A of R. We say that it is a compact set, or we say that it is compact if every open cover of A admits a finite subcover. Right, so that's the definition of a compact set. If every open cover of A admits a finite subcover, we call it compact. So the Heine-Borel theorem says precisely that every bounded closed interval is compact for all real numbers A and B. Right. So admittedly, compactness is an abstract concept, but we can characterize it in a very concrete way, which is the main theorem of this lecture. So here is a characterization. Let A be a non-empty subset of the reals, then it is compact if and only if it is closed and bounded. Now both of these are very, very concrete notions, even though this is a fairly abstract notion. So this abstract definition is actually same as a very concrete one. Okay, so let's start with the proof. So first assume that A is compact. And we want to show that A is closed and bounded. So first, let us show that A is bounded. So consider or define this set C, fancy C or script C, as the collection of all these open intervals. So for each natural number n, we have this open interval, which is nothing but the open interval which is centered around the origin and has its end points as minus n and n. So we collect all of them, and clearly they are growing. So this is for n equals 1, this is for n equals 2, then for n equals 3. So this is in fact an open cover of the entire set of real numbers. And hence in particular, this is an open cover of A. This is an open cover of A. Okay, we observe that. And therefore by compactness of A implies that there is a finite subset of D of C such that D covers A. This is immediately from the compactness. Alright, so there is a finite subset D of C which covers A, but this implies that A is bounded. So I will justify a little bit, but I'm sure you can see it. This implies A is bounded. So let me say it in words. Since there are finitely many things of this sort whose union covers A, let's say n1, n2 up to nk are natural numbers such that the union of these intervals covers A, but then this union is itself a bounded set because it is contained in this thing where ni is the greatest among all these natural numbers. So just to make sure you understand this implication, so we see that A is bounded. Fine, now we show that A is closed. To that end, let's draw a diagram. So this is the entire set of real numbers, and here somewhere we have our set A. Let's say we denote it like this. This is A, and to show that A is closed, we pick something outside A. Let's say X is outside A. Okay, and to finish the proof, or rather to show that A is closed, we need to show that there is some open set around A. There is some open interval around X which is disjoint from A. In other words, or in said another way, to show that A is closed, we need to show that this is open, which means that whenever we choose a point in it, there should be some room around this point which is contained here, which is to say that it is disjoint from A. So we need to find some epsilon such that this open interval x minus epsilon comma x plus epsilon is disjoint from A. So that is what we will do. So to do that, for each A in capital A, we can find epsilon A greater than 0 such that this intersection is empty. Which intersection? So why is this? This is very simple. You pick some A in capital A. Since it is distinct from X, X being outside A, it is distinct from X, you can choose some small epsilon such that the corresponding open intervals are disjoint. In fact, you can choose epsilon to be half of the distance between A and X. Fine, so we can do this. And now define script C as the collection of all these. Let's call this something so that we don't have to write too much. Let's give this a name. This thing will be called UA, and this thing will be called VA. Okay, so define C as this collection, right? And again, this is an open cover of A. Why is that? This is an open cover of A because each element, you pick some element of capital A, it is there in this, and therefore the union of all the things here contains A. So this is an open cover of A, and again by compactness we get that there is a finite subcover of this, same thing as previous. So I will repeat this. So there is some finite subset D of C such that D covers A, but I would like to write it a little differently. This statement over here can be rewritten in a different way, and let me erase it and write it so that I don't have to turn over a page. So an alternate expression of the same is there is a finite subset f of A such that this is a cover of A. So please make sure that you understand this implication. The set C was indexed by A, and a finite subcollection of this therefore will be indexed by a finite subset of A. That is what we are calling capital F. All right. And now note that, or maybe consider or define V as the intersection of these things. So what is going on? Let's say, just for the sake of understanding, this is a two-element set, which is A1 and A2. So let's say A1 is somewhere here and A2 is somewhere there, and there is some interval around it such that the corresponding interval around X is disjoint from it. And there is some interval around this such that the corresponding interval around X is disjoint from it. So if we intersect these two intervals that we got, the intersection of those two intervals would be an open set around X, but that will be disjoint from both of these guys and hence from A. And that is the idea of the proof. So we are just executing that, right? So this, we claim, this capital V, of course, is a non-empty open set. It is non-empty because every VA contains X, and hence this thing contains X. This is non-empty. But V is the intersection of finitely many open sets. F is a finite set. And V is the intersection of finitely many open sets. And hence V is open. So we need to be very clear about this, that we have shown that this is an open set. Open set which contains X. Right? So let me note that here also, X and V. So we have argued these things. All right. Finally, we want to show that this is disjoint from A. So finally note that VA intersection UA is empty. This is by the choice of epsilon A. This is empty for all A in F. And therefore, V intersection UA is also empty for all A in S, which implies V intersection union, this is also empty. So this equation implies that if V is disjoint from everything of this sort, every UA, then it is also disjoint from the union. But this union contains A because this is a cover of A. So since this is a cover of A, this contains A, and therefore V is disjoint from something that contains A, and hence V is disjoint from A. So there is some open set V around X which is disjoint from A, and this is what we wanted to do. So this shows that A is a closed set. So I did not write everything, but I hope that whatever I said was clear to you, and I encourage you to write all the details in your notes. All right, so we need to do the other direction now. We need to now assume that A is closed and bounded and show that A is compact. That is actually easier. So now assume A is closed and bounded. Okay, we want to show that A is compact, so fix some open cover. So let C be an open cover of A. Okay, we want to show that C has a finite subcover. All right, now by the boundedness of A implies that there exist A and B in real numbers with A less than B, and this is contained there. That follows from boundedness of A. And yeah, so now define C prime as C union this open set. So again, note that this is an open set. Why is that? Because A is closed. A is closed implies the complement of A is open. So C prime is an open cover of this guy now. Alright, in fact, it is an open cover of the entire set of real numbers, but in particular, C prime is an open cover of the closed interval A comma B, which implies, by high-neighborhood theorem, that there is a finite subcover of this thing. So let D prime, or there exists a finite subcover right? So that's by the high-neighborhood theorem. And say we may assume that D prime is equal to D union this set where D is a finite subset of C. So a finite subset of C prime could just be a finite subset of C, or it could be a finite subset of C along with this guy. But there is no harm in including this, because after all, we just wanted to extract a finite subcover of C prime. And adding one more extra element is not going to either disturb the finiteness or the openness, because this is an open set. So all I'm saying is that C prime was an open cover of the closed interval A comma B. By the high-neighborhood theorem, we may assume that, or we deduce that, there is a finite subset D of C such that this constitutes an open cover of the closed interval. Okay? But then, since this is an open cover of the closed interval A comma B, this is also an open cover of A, because A is contained in the closed interval A comma B. Right? If something covers a big thing, it also covers a small thing. But again, this has no contribution to that covering. This is disjoint from A. So we deduce that actually script D is an open cover of A. But script D is finite, and hence we are done. So all we wanted to do was show that this has, there is a finite subset of this which covers A, which we have done. And that's it. So that proves that A is compact. So all we have done is basically generalize the high-neighborhood theorem. The high-neighborhood theorem said that the bounded closed intervals have this property that every open cover has a finite subcover. We have generalized that to closed and bounded sets. We don't necessarily need to restrict ourselves to just closed intervals, bounded closed intervals. We only need closedness and boundedness. All right, so that's a very, very nice theorem, very, very useful theorem. And it has a corollary that if you have a compact subset of R, then its infimum and supremum both lie in the subset. And this will be an exercise. Very, very easy exercise. Okay. And with that, I want to end this lecture. As usual, like, comment, share, subscribe, and I will see you next time.